In this sample, we're going to find out how much energy we have to give to a satellite in order to put it into a given orbit. So this references a past example from chapter 6, where we talked about circular motion. We've got a satellite with a distance from Earth's center of 4.22 times 10 to the 7 meters. So that was nice. We don't have to add Earth's radius or anything in there. We're told it has a velocity of about 3,000 meters per second. And we're told that it has a mass of about 3,500 kilograms. So how much energy is needed to get it up into orbit? So the new formula, if you will, that we have from this section is E equals negative, and there's our universal gravitational constant, the mass of the Earth times the mass of the satellite divided by 2r. So, okay, it's going to have two kinds of energy. It's going to have kinetic as well as gravitational potential energy. And we know that our gravitational potential energy for objects that are not near Earth's surface was negative, big G times the mass of the Earth times the mass of the satellite divided by r. So I calculated that for what it needs to have in space and what it needs to have on the launch pad. So the amount of energy that we have in orbit here, okay, using big G, mass of the Earth, mass of the satellite, and then the radius that it's in orbit, we get a negative 1.65 times 10 to the 10th joules. And I'm going to come back to that in a little bit. So on the launch pad, okay, we can still use this formula on the launch pad using making r the distance from the center of Earth. And in this case, it's just, since it's on Earth, our r is Earth's radius. So what I get for this is negative 2.19 times 10 to the 10th joules. So this is what it has on the planet. This is what it needs to have when it's in orbit. So in order to get we need to add some energy to get it from negative 2 up to negative 1.65. So the amount that we need to add to get it to that, we need to add the difference there, which is 2.02 times 10 to the 11th joules. That's what we need to add to it. And we've done problems like this before, where then we said, okay, well, if we add all kinetic energy, we could do the 1/2 mv squared to find out what speed we need to launch it at. So that's sample 4. I'm not entirely sure how much we're going to use this, but I wanted to include it.